To build systems that reliably navigate real-world complexity, we must first define the exact structural taxonomy of artificial intelligence. At the outermost layer sits artificial intelligence, the broad umbrella term for systems mimicking human cognitive capabilities. Inside, we classify tasks associated with biological intelligence: perception, reasoning, learning, problem-solving, and decision-making. But the crucial transition occurs when we stop hard-coding rules and enter machine learning. Machine learning is a specific subset of AI where systems are fed large training datasets. By processing this data, models iteratively adjust their internal mathematical parameters, allowing them to optimize their performance on a given task without explicit programming. If you attempt to write static if-then rules for millions of edge cases, the architecture collapses under its own weight. Data-driven discovery provides the necessary scale for intelligent systems. Within machine learning, we isolate deep learning. This is a highly specialized discipline built specifically to handle the multi-layered complexity of unstructured data, like raw text, audio, and high-resolution images. Deep learning operates on the architecture of multi-layered artificial neural networks. These are computational models directly inspired by the biological networks of neurons and synapses in the human brain. The term deep is literal. It refers to the utilization of multiple hidden layers of learning. Data passes through these consecutive layers, allowing the network to build hierarchically rich representations of the input features, moving from basic edges and shapes to complex semantic concepts. At the absolute center of this taxonomy, we find generative AI. Standard machine learning is generally discriminative. It classifies or predicts existing patterns. Generative AI utilizes massive, multi-purpose foundation models, pre-trained on vast datasets, to create entirely new, high-fidelity text, code, or images that share the statistical characteristics of their training corpus. Recognizing this nested architecture, moving from broad logic to the specific learning parameters of ML, and finally the raw generative power of deep foundation models, is the first step in competent system design. Training the massive architectures powering modern natural language processing presents an immediate data problem. Human labeling is impossible at the multi-terabyte scale these models require. To bypass this bottleneck, we rely on self-supervised learning. In this paradigm, the system autonomously generates its own pseudo-labels directly from raw, unannotated data. The system achieves this by formulating pretext tasks, which use the inherent structure of the dataset to define the training objective. For example, the system will take a raw sentence, deliberately mask a word, and train itself to predict the missing token based entirely on the surrounding context. A single guess achieves nothing, but executing millions of these pretext iterations forces the model's internal weights to map the deep syntactic and structural rules of the language. This cumulative statistical mapping allows the model to build multi-dimensional representation vectors of how words relate to one another. Through this process, the system achieves complex semantic understanding without ever receiving an explicit human-provided label. When we shift from language modeling to systems that must learn through sequential decision-making, we use reinforcement learning. This operates as a strict feedback loop. A mathematical agent observes its current state and then executes specific actions within an external environment. The environment responds via a mathematical reward mechanism. We establish penalty values for mistakes, like a drone colliding with a wall, and high positive rewards for completing the operational goal. The agent continuously updates its policy to maximize cumulative long-term gains. We apply this exact logic to language models to align them with safety criteria and stylistic preferences, a pipeline known as reinforcement learning from human feedback, or RLHF. Step 1 is supervised fine-tuning. We update the base model on a strict dataset of high-quality human demonstrations to establish a baseline of expected behavior. Next, the model generates multiple responses to a prompt, and human reviewers rank those outputs from best to worst. We use these rankings to train a distinct secondary reward model. Finally, optimization algorithms utilize that reward model to mathematically update the base language model's internal policy. RLHF is a translation layer. It takes abstract human concepts like helpfulness or safety and converts them into rigid mathematical constraints the model must obey. A trained model is useless in a production environment unless its error rates can be mathematically verified. This grid represents the confusion matrix, the standard evaluation tool for categorical classification tasks. The matrix maps the actual, ground truth reality against the model's predictions. This allows us to instantly evaluate the correct predictions while isolating the false positives and false negatives. From this, we derive precision, the ratio of true positive predictions to all positive predictions made. We prioritize precision when the cost of a false positive is catastrophic, like incorrectly classifying a legitimate transaction as severe fraud. Conversely, recall measures the ratio of true positives to all actual positive cases in the dataset. We optimize for recall when missing a true positive is dangerous, such as failing to detect a critical medical anomaly. When an architect is dealing with severely imbalanced datasets, they rely on the F1 score, which calculates the harmonic mean between precision and recall to provide a single, balanced indicator of system health. The decision to optimize for precision or recall represents a specific business risk strategy. Every mathematical weighting in the matrix translates directly to a real-world consequence. This curve evaluates the AUC-ROC, the area under the receiver operating characteristic. We use this to evaluate a classification model's performance across multiple threshold limits simultaneously. By plotting the true positive rate against the false positive rate, systems architects can visually identify the exact mathematical threshold that best serves their required operating parameters. Categorical metrics fall apart, however, when we shift to regression models. These are systems designed to predict continuous numerical outputs, like temperature, latency, or financial value. Here, we track error margins. Mean absolute error, or MAE, measures the average absolute difference between predicted and actual values. Alternatively, we calculate the root mean squared error, or RMSE. Because RMSE squares the errors before averaging them, it exponentially magnifies large deviations. Architects heavily favor RMSE when they need to severely penalize massive outlier errors in their predictive models. Standardized evaluation through these matrices and curves provides the mathematical proof required to turn a raw model into a predictable, deployable asset. Once a model is mathematically validated, it moves into production to execute live predictions. We call this deployment phase inference. Architects must choose an infrastructure that matches their data velocity. Real-time inference prioritizes millisecond latency for immediate single transactions. Batch inference sacrifices that immediate latency to maximize bulk data throughput, processing massive datasets all at once. For workloads generating massive payloads, up to a gigabyte of data, we deploy asynchronous inference, utilizing deep queue architectures to decouple client requests from long processing times. We also face geographic constraints. Sending data from a remote device to a centralized cloud LLM yields high accuracy, but it requires persistent network connectivity and introduces unavoidable latency. The alternative is inference at the edge. By deploying optimized small language models directly onto local microchips and hardware, we achieve zero-latency, offline functionality, sacrificing total model capacity for absolute speed and reliability. A mathematically perfect model will still fail in production if the chosen inference architecture doesn't match the physical reality of the network. To manage that deployment at an industrial scale, we rely on MLOps. This is the structured pipeline that ensures machine learning models are deployed, monitored, and retrained systematically. The foundation of MLOps is strict version control. If a deployed model begins producing severe errors, architects must have the immediate capability of rolling back the data, the codebase, and the model weights to a previous stable state. We standardize these deployments through continuous integration of tests and continuous delivery of code, ensuring that the transition from a local engineering environment to a live server is completely automated. Once live, the model remains under continuous monitoring. We are constantly searching for model drift, the inevitable degradation in accuracy that occurs when the statistical properties of real-world data shift away from the original training baseline. Detecting this drift must immediately trigger automated retraining loops, pulling in fresh data to continuously update the model's parameters. Reliable AI requires a living CI/CD pipeline, supported by the relentless operational discipline of MLOps to survive in a dynamic environment.